Hi, this is Alex from devstories.eu. PySpark Fundamentals, episode 15 of 21. You write a custom function in Python, plug it into your data pipeline, and it works flawlessly on a small sample. But when you run it on the full dataset, the job slows to a crawl while CPU usage spikes. The code itself is fine, but you are paying a hidden execution tax. Today we are talking about extending Spark with Python UDFs. A user-defined function, or UDF, allows you to execute custom Python logic directly on a Spark data frame. You use this when the built-in Spark SQL functions do not cover your specific business logic. The process is straightforward. You start by writing a standard Python function. For example, you write a function that takes a text string, applies a complex custom formatting rule, and returns the modified string. To make Spark recognize this function, you import the UDF function from the PySpark SQL Functions module and apply it as a decorator directly above your Python function definition. You also pass a return type to the decorator, such as a string type or an integer type. If you do not provide a return type, Spark defaults to a string type, which can cause silent data issues if your function actually returns a number. Once decorated, your custom Python function acts just like a native Spark function. You can pass it into DataFrame operations like a select statement, feeding it column names as arguments. Here's the key insight. A standard scalar Python UDF operates strictly one row at a time. It takes one or more column values from a single row as input, evaluates your custom Python logic, and returns exactly one output value for that specific row. If your data frame contains 10 million rows, your Python function is invoked 10 million separate times. This row-by-row operation is easy to reason about, but it creates the massive performance bottleneck we mentioned at the start. To understand why it is so slow, you have to look at how Spark executes code under the hood. Spark is built in Scala, meaning its core engine runs inside a Java Virtual Machine, or JVM. Your custom UDF is written in Python. The JVM cannot execute Python code natively. To apply your UDF, Spark is forced to spin up separate Python worker processes alongside its own executors. It then has to physically move the data out of the JVM memory space and into the Python process. Spark relies on a Python serialization library called CloudPickle to handle this complex transfer. This is where the performance tax is collected. For every single row in your dataset, Spark serializes the inputs in the JVM, sends that binary data across a local socket to the Python worker, and deserializes it into standard Python objects. Your custom function finally runs on those objects. Then the whole cycle happens in reverse. Python serializes the output value using CloudPickle, sends it back over the socket, and the JVM deserializes it back into Spark's internal memory format. This constant serialization and deserialization between Java and Python is incredibly expensive. The real cost of a standard Python UDF is rarely the logic you write. It is the silent overhead of translating data back and forth between two entirely different runtime environments on every single row. Thanks for spending a few minutes with me. Until next time, take it easy.